starting to record. We can start. Okay, so good evening, guys. Okay, it's only mobiles. Okay, can you hear me, sir? Hello?
Uh, I can hear you.
Okay, and you can see my screen, right? Hello?
Yes, I can see your screen.
Okay, thank you. So basically, I'll try to run through my thesis and the drawings. I'm going to open this one, architecture and the structure. Okay, just wait for a moment. Okay, this is the structure. This is architecture. So just I think this is swap. Okay. Hello. I'm just speaking to myself. I'm just checking.
I can hear.
Okay. If I'm not clear, please you can let me know if I should raise my voice
Okay.
or not. Yeah. Okay. So these are architectural drawings of my thesis project. Then these are structural drawings. I did POW foundation, though it was like a four-story building, but my professor said I should incorporate a POW foundation because this structure was under seismic zones where it's prone to earthquake 7.8 to 8 degree. Okay, so I'll open my thesis. If there's anything that you'd like to ask, this is my thesis. So do you need me to go step by step, you know, going through, or there is a specific area that you need me to focus on?
Let me go to the part which you should start from. Uh,
Okay, so this is the context page. Usually, actually, I did it in parts. Uh, okay, we have a frame structure design, uh, which is the project background, estimation of cross section dimension. Here, I was using my references as a Chinese code and some ACI. So, but ACI, but Chinese code is almost like 80% this. Um, but it's not. There's no much difference. It's just some few. I mean, digits that are a little bit different, but it's just the same thing. So beam section, column section, slab thickness. I'll show you how I estimated the beam section and column section, slab thickness, and so on. Then we have the design data, structural plan, floor roof design, load calculation, roof design. So on this part of this structure, my supervisor advised that I should select only one section, which is section, if we come here, section C, section C, not section C, but axis C, axis C. Why? Because he said that if you do all of this A, B, C, it will be very, very, very tedious. So he said to reduce the workload, you just choose an axis that you work the framework, um, the for slab reinforcement, beam reinforcement, column reinforcement, and so forth. So I so this building I had to also um, design for like horizontal load, which is earthquake load. We'll see it at the end. So I choose axis C. So axis C, and for the column reinforcement or column analysis, I had to choose the one in the middle, which is actually having experiencing loads from all this direction, from this beam, this beam, this beam, this beam. So I had to do what we call a tributary area. To create a tributary area, then you see that it has got a large section than the other two. All right. Um, okay.
A question, and then
Mhm.
I've got a question. Can you go back to your drawing?
Mr. Schuler has got a question. Oh yeah.
So let's see. On the architecture, is this a corridor? Is this like a passage?
Yes, it's a corridor. Yes. Yes.
This one is very
On the ground floor already. Yes, it's the ground floor.
These are elevations.
The elevations, yeah.
Staircase.
Staircases. Mm.
So this is the first floor.
This is the first floor, yes. Yeah.
I'm just interested. My question is, this span is longer than this one, isn't it?
Hmm.
They just decided to put one.
Yes, they just decided to put one, and this one is a beam, is a girder.
Which one is the main? This one here.
Yeah, this one. See this one from. Yeah, it was crazy.
Let us try to check
Other dimension.
the span.
This plan.
I don't know whether you're not talking, but I can't hear you. Or you're talking, but I can't hear you.
Okay, it's Mr. It's Engineer Schuler who is asking a question. So he's saying that he wants to check the span
Okay.
from that column to yeah.
So these are 5, these are 8.
So we can see that that span is five something, almost six, and that one is eight. All right. So on the corridor, see on the corridor here. Okay. Alright. So on we have 1, 2, 3. So this one is the largest span than this one. Okay, that's how we designed it. Then this one is the main gate. This one was the main gate. This one was the secondary. Yes. So this is the main getter which connects from this column to that column. This is the main getter, and this one is the secondary beam. And these are circular columns? Yes, these are circular columns. These ones are circular. Okay. Yeah. Okay. So for the purpose of this design thesis, so firstly I said I had to choose only one axis, also for beam reinforcement, for column reinforcement, and slab reinforcement. So everything was like everything was determined by that axis. Whatever that I designed, it was like a sample for the whole structure, the whole building. Okay. Okay, let me just dive into it, so that we can quickly follow. So these are architectural details. Is the roof slab. Also for the slabs, I only design the roof slab.
I think you can skip to.
Okay. Okay. This is the drawing that you have sent Mr. Schuler, right?
That's the one I sent. That's the one I sent.
Okay. Okay. Let's go down. So structural details, live load, roof accessible to 2.0, standard live load value for floor 2.5. So I designed roof slab and floor slab. So roof slab was on its own. Floor slab um, was also catering for all the floors from the ground floor up to the third floor. Yeah. Okay, then I was using HRB 400. That's for steel bars and stirrups. But this is Chinese, right? Yeah, it's Chinese. This is Chinese C25, C30. Okay, let's go down. So beam section estimate. Okay, the height of the primary beams or girders determined according to H, 1 over 15 to 1 over 10 multiplied by L. So I input from span 2 to 4 on the drawings. So yeah, so from span 2 to 4, right? So from span 2 to 4, 8.1. Okay, then I input the formula. This is the formula that I use, or the range of the estimate. Then I get 540 to 810. Then I chose 700. 700 as my edge. Span B to C, as shown on the drawing as well. Then I chose 600, 480 to 720. I chose 600. Then same applies. I chose 600. Same applies to this span. I chose 600. So reason, what is the reason? Choose 600 as the height, since the maximum span of this section is 7.2, and also consider the safety requirement. The choice for span D to F, the height is less than maximum required calculation. H is greater than 450. So you see, in all my calculations for this span, I chose 600. This one I chose 600 because it was in between 480 to 720. So it's just a choice. Uh, then if it fails, then you have to take the one which is higher. For example, this one 720 for this span. But just to create uniformity, I just chose the height as what? As 600.
There it says the height is less than the maximum required calculation. You say it should be greater than 415. Where is the 415? Well, that's for span 3 to
415, this one. So here, this statement, it says that h is greater than 415. So 415 is the minimum. If you see, for all the spans, is the minimum. So here I could not choose what? The minimum. I had to choose 600, which is you know catered for with the largest span, which is like 8.1. That's why I chose 600. All right. That's all. These are the calculations for the beams to get the heights. Then secondary beams, same applies, but now I did not use this one. For secondary beams, the formula is this one, 1 over 18 to 1 over 12 with the span. L is the span. So span B, B asterisk, which was this one, B. The B asterisk is between B and C. This one, this one. So these are the secondary beams. So B asterisk 3.6. So I choose the height. Same applies because the height should be H should be greater than 300. For safety of the beam, I choose 500. Likewise. Then for B, which is the breadth, the formula is 1 over 2 to 1 over 3 H. H, which is the depth of the beam. Same applies. You input the values, then you get it runs from 250 to 167. I chose 300 here because where is it? Because here the span, this one for this height, is 300 to 200. For this height, 700 is 350 to 233. So I choose, since I had this 1, 2, so this one I automatically chose. Even this one is less. I had to choose 300. Yeah. For column section, we have a formula here, N, which is a design value of axial pressure or force on the column. That's, yeah, it's represented by N. Beta, column axial pressure coefficient. Yeah, everything I had to put all the definitions of these parameters. All right. Where AC is the cross-sectional area of the column. So when I get my N here, I input it here. Over, this is the coefficient axial compression ratio limit value. FC, that's design value of concrete axial compressive strength. So when I get my N here, inputting all the value, tributary load area on the simple supported column, then I think the diagram is here. This is the diagram of the tributary area. So the tributary area, half of this, half of that in both directions to get. So you see that this column had experienced uh, the actual load is quite high than 1, 2, even if we get to even this one, because this one only here, this part, this one you can only get the tributary area from here. So this worked as a typical, you know, example for all the other columns because it's experiencing the highest actual load. So if we use this one, which means if you use it on this one, we're able to design enough reinforcement for this one. Though it is a, it's getting less actual load uh, compared to this one. So kind of like maybe over design or something like that for the column reinforcement, but it will be still okay. Okay, so these are all the calculations. We're using FC as 14.3 megapascals, which you said it was quite low, isn't it? Yeah. Okay. Any questions so far?
I think that part is clear.
It's clear.
Maybe start from page 10.
Okay. This part is clear as well. Slab thickness.
Yeah, this part.
Okay. Okay.
Yeah, yeah.
All right. All right. We jump from there. This is just the presentation of the beams. You can see. Sure. Yeah.
I've got a question there
Yes, please.
on page 9. Mm, why didn't you pick for the corridor? Why didn't you pick maybe 3,600 by 2,100?
Which one? On this one?
Yeah.
Why did I pick
Why didn't you pick? Because if you go to table 3.2, which is on page 10,
page 10?
you picked the other side and not this side.
Oh, here. I picked 4,156,000.
No, you on page 10,
Page
table
10.
3.2. Yeah, 3.2.
Oh, this one. Okay.
Yeah.
Uh-huh. You're saying I didn't pick the 2.1.
Why didn't you pick? Why didn't you pick the 2.1 and the 3,600?
Okay, let's go again here. 2.1 and 3,600. Oh, this slab.
Yeah. Yeah.
Didn't
Yeah.
didn't I? I think I think I did somewhere. Let me check.
You picked the one which is 4.15.
4.15. Let me see.
Yeah. Meaning you did the other side of the right side of the picture.
Okay. Well, 4.15. 4.15 and oh, so 2.1 and
Yeah.
3.6. Okay, okay. You know why? I picked I picked
Mm-hmm.
the maximum span on this one.
Oh, you picked the
At the
maximum span.
maximum span, yes. I picked up the maximum span for because that one will give me higher moments, especially on this one. It will give me higher moments.
Oh,
So I
okay.
had to pick everything that I had to pick. I had to pick with highest moment, highest shear, highest axial, so that it will be
Okay.
a
Okay.
typical, yeah, it will be typical for all the floors. If I have high moments, let's say if I have high moments on this slab, which means my reinforcement on this slab, it will cater for that because it has got actually a small span. So
Okay,
it
okay.
will be good. Yeah, just for safety. Yeah. So that's okay.
Yes, that's fine.
Okay, thank you. Thank you. Thank you for that observation. So I think here we've passed. Okay. Mm, there's also what Engineer Shula. Okay, here I remember now. I think you sent a screenshot about this part, right?
Yes, yes.
This part. Okay, this part, Engineer Mkubesa. Um, so my floor slab live load 2.5, right? We together the QK.
Yes,
Usually in Chinese they
yes.
use Q and G. British standard is what?
Okay.
Is D and what? And L, right? D for
Yeah,
dead
yeah,
load, D for dead
yeah,
load, L for
yeah,
live load. In Chinese they use Q,
yes,
they use Q for live load and G for dead load.
yes.
Yeah. So okay, according to the elastic theory design, the load design value. So according to the Chinese, well, as I said, there is not much difference, but you see, there is Q1, 1.2D plus 1.4L, right?
Mhm.
So I got 8.95. Then I had to use another. This this incorporates the seismic load coefficient. This one,
Mhm.
it incorporates the seismic load coefficient, which is 0.7, according to the Chinese design. Because I had to go on the table.
Okay,
If I had the picture, I would have shown you, but I'll look for it. If I have it, I'll share with you. There's a table values that you have to
okay,
check that this magnitude of earthquake goes with this coefficient. So therefore,
okay, okay,
you incorporate the live load and the coefficient of the seismic load, which is the lateral load.
okay,
So it's 1.35 by 4.54. So this was, if we incorporate the coefficient of seismic load, how is that the load, the the combination of load is gonna be? So here you see the normal one, which we are used to. It gave me 8.95. I think there's someone
yes.
who wants to join. Or it's Paul. Hello, Mr. Paul.
Hello, good evening.
Good evening, Engineer Paul. How are you?
I'm all right. How are you?
I'm doing very well. Thank you. So you just you just joined us while I'm just going through my uh, thesis design project that I did back then in the university. So Mkubesa had some questions that he needed clarity on. So that's what we are going through. That's what we are browsing through at the moment.
Okay.
Yes. So we're just going through it and just, attend to the questions that he had and so on. So if probably could add some questions with you, then if you have some contributions, then you can add on. I think I'm not gonna take much time just to explain, and give clarity to Mr. Mugubesa's questions based on this thesis project.
All right.
Okay.
Okay, no problem.
All right. So I was here. So in comparison of the above calculation, accordingly, since Q1, so I was explaining to say this one is the normal one, and this one is the one that I incorporated the seismic load um, coefficient. So I found out that 8.95 is higher, which means Q1 is greater than Q2. Therefore, the combination controlled by the live load variable is selected. So then, therefore, I selected Q1. All right, I
Okay.
selected Q1, which is higher than Q2. But if Q2,
So
sorry,
is it in Zambia? Is it necessary to add the 0.7?
no, I don't think it's necessary
So
because
it's
like Zambia, I don't think it experiences earthquake or too much wind loads. I don't think so.
okay.
Yeah, I do not. I don't think. I think that one it can be left out unless because this was like just a four-story building. So a four-story building here in Zambia, I don't think you have to include that coefficient because uh, Zambia is not prone to any earthquake or high wind loads unless it is a
Okay.
high-rise building, maybe like 20 floors and above. Then eh, I think then we can incorporate like wind loads. But seismic, no, I do not think so.
Okay.
Probably to due to climate change, probably in the next maybe 3 decades. I'm not sure, but for now, I think it stands as it is that no seismic zones associated.
Okay.
Yeah. So, but this project, um, I had to design this structure under the seismic action or
Okay.
in the seismic
Yeah.
zones. Yeah. So it was quite complicated structure because seismic seismic is dynamic. You know, it's dynamic, and when you're doing a hand calculation, it's quite tedious. It requires a lot. It requires a lot. Yeah. So that's basically it when it comes to here, and I hope I have clarified uh, the questions that you had.
Yes, you have.
Yes, thank you. So here it was just comparison, and even as well here, like you have to compare G plus Q over 2, the other half, the dead load, and half of the live load. What do you get? Then you also take the maximum. There are some cases whereby the live load will be actually quite high, depending on the variables here, like the the earthquake load. They're different. They're different parts. So I had to use this code. There's the whole table that you have to. So I chose just one section. So that's where I was deriving all these values from. Okay. We do the calculation of the span, short span direction, L01, long span direction, L02, and you find out that even the parameters they are a bit different to the BS standard. the British started because L01, L02, this usually exists in the because in BS I think it's just length width. Yeah, it's length is if it's length it's length, it's width is width or breadth. Yeah, something like that. But Chinese they also incorporate those usually breadth. They use B as a parameter. Okay, let's move on. So this was the bending moment calculation. Bending moment calculation. MV1, um, where V is the Poisson ratio. Okay, so the Poisson ratio was 0.2. So or M1V or MV1, it's up to you. It's still okay. Then it's equal to
So how do you pick the Poisson ratio?
the Poisson ratio. You pick the Poisson ratio based on the. I had also it's also in the design Chinese design code. How you pick the Poisson ratio.
So
The
if
Poisson ratio also, I think it depends with the span. I'm not quite sure. It's been a long time, but if I do a revisit, I think I'll check some of my Chinese code books or PDFs and check.
I, I think it's in the Chinese codes. I think
It's in the Chinese code,
I
right?
right. Yeah.
Yes. I don't think we like in the BS we have this kind of you know mm, it exists in the Chinese code. I've been checking the BS, the ACI. I've never seen this though. But in this case,
I,
my professor had to he had to make me use the Chinese code, mostly the Chinese code. Um, I used a little bit of ACI in this design project, but you mainly emphasize on. So I was using Chinese code throughout, as you can see. But there's just a little difference, maybe 0.5%, I think, of all this calculation. So you can see here, check the bending moment coefficient of two-way slab from the deflection and bending moment coefficient calculation table, table 7.6, reinforced concrete structures, Chinese version. You see that? This is the Chinese version that I was using. Okay. So according to that's the design to know whether it's a two-way slab or one-way slab. I think we all know that. So we go all these calculations. It's just for calculating the bending moment, and this one was on the floor slab. So I was just selecting a few. If you can check on my drawing, if we come here, this. I think this is the part that I only choose for the slab because I wanted to cater for the slab. For the column, I chose axis C. For the slab, I chose these that have numbered 1, 2, 3, 4, 5, 6, 7, 8, up to 15. Okay, so they are numbered in that manner. Quite confusing, but I think you'll get it. All right, let's go back. So this is the presentation of axis D and F 1 and 2. Uh, here, according to the code as well, here it's fixed, fixed, fixed. Here, I can't remember of the code. Was it if it was should be fixed as well. Mm, I will have to go back to the design, the Chinese design code. But they have this kind of setup of all the slabs, whether it's fixed on one side, whether it's fixed all the sides, or whether it's a cantilever. Yeah, something like that. Okay, let's go down. So these were the calculations of the moments. M1U, M2U, which is here, M2U in this direction and in this direction. The Y direction, the X direction. That is inside the moment in the slab, in the middle. What are the moments? Okay. Then on the supports we have M M1U, M prime 2U in that direction. Y direction, X direction. So if we take like a section from here, you see that we have this support, this support. If we take a section this side, we have this support and this support. And here we have a deflection. You know that the bending moment diagram, we have a deflection here. If we also cut from here in the y direction, we also have another a bending moment diagram, also a deflection there. So these are all the calculations for the moments. Okay. Then we do the reinforcement. The reinforcement, you choose H01, H0, you choose the maximum, you choose H0, which is 90 here. And all this is provided in the code. Like for example, the minimum concrete thickness of the environmental category slab is H is equal to 15. Assumed steel bar diameter 10. For short span direction, effective height, and so on and so on. So all these calculations, they come from the Chinese code. It's just a matter of choosing to say, okay, diameter 10, this, then you input, you get the highest, so that you can have enough reinforcement, whether in the slab, or in the beam, or in the column. So this is the area of steel reinforcement, bars with the formula given. Input all the details, necessary details, as much as you can. 0.9, which is gamma. All right. For the calculation, the arm coefficient of the internal force is gamma, which is 0.95. Then we have 6.8. So I was getting these values from here, from all my calculations here. All right. So we have the positive moment and we have the negative moments accordingly. Then I calculate. This is from the Chinese code, because after calculating all this and find out that from here the maximum is 387 square millimeters, then this one is the minimum, AS minimum. So if you calculate 0.2% multiplied by 1000 multiplied by 90, which is the H, the depth, effective depth actually. That's the effective height, right, of the slab. Am I right? Yeah, of the slab. Then you get 180. Therefore, compare with the above calculated results and take or choose the larger value for AS. So the larger value for AS, if you see here we have 180. So the larger value is 350. 350, yeah? So I had to choose diameter 8 at 130. That's what I had to choose. Okay. Right. We go ahead. Same process. Same process. Repeating the same process, but for different what? For some were the same, some were different. I think this is D one. If you go to the drawings, I'm just using this drawing. D, where's D? D is here. So it was this part. So I chose this part here. Okay. So this is this part. Fixed, fixed, fixed. This one, I forgot this one. Three sides fixed. Oh, that's hinge. So I specified here. So this one is a hinge. It's a hinge format. This one. This one is a hinge. Okay. I got the answer here. All right. The same calculations over and over again with different slab. You see how it's done. Then the reinforcement. Then I apply again this one. Then choose. Then again another section or portion. I do the same thing. Calculate the moments. Calculate the reinforcement, the area of reinforcement, and then choose the area of reinforcement and choose the rebars and how they are spaced. Okay, then this is a roof slab. There I was doing the floor slab. This is the roof slab. Same applies, the same thing, same format. This will be a little bit different because this roof it's accessible. Maybe there's air conditioning and stuff like that. Yeah, so calculate the dead loads. This was 7.73, and I remember for the four floor slab, it was 4.54 somewhere there. So it's the same process. So I picked the roof slab and one symbol of floor slab and did all these calculations the same way. All right, reinforcement for the slab. Any questions, guys? Feel free, guys. It's not me who is just talking, but feel free, guys, to input whatever that you have in your mind. But basically, that's how they calculate. That was slab reinforcement, the floor slab and the roof slab reinforcement, and all the calculations, those tedious calculations, and calculating took me a lot of time. Yeah, but well, it's uh, it's actually necessary and important that you get to know how it's done, how the calculation, all these calculations are done, so you have an idea. Even when you're doing with the software, you have you have an idea of how you are deriving your figures, your values, and also with the aid of the aid of the code, whether it's British Standard, ACI, certain values you take, you input, and you know um, exactly what you are designing. Okay, so any questions so far?
No, no questions for
No,
now.
no questions. Okay. Should we continue or we'll do the other part of the rest tomorrow? Because now we have to go
I
now
think we can.
on the dead and live load internal force calculations.
Why can't we do it like maybe a day after tomorrow so that we
Okay,
pass through the other stuff as well?
that's not a problem. That's not a problem at all. I'll just talk to Mr. Shula if he can also create
Okay,
another 30 minutes for us to go through it.
okay,
But so
okay.
far so good, right?
Yeah,
Mr. Paul. Yeah, man.
I'll have to watch the recording because I think I missed
Oh,
most uh part of the video.
okay. But well, you didn't miss much. It was just almost at the beginning of you know it wasn't much that you've missed
Okay, but hopefully you post the video on YouTube so that you can just go back and watch.
there. Okay, no problem, no problem. I'll let Mr. Schuler to upload the video tomorrow
All right.
or today if he can, if he has time. But I'm sure it's tomorrow. So okay, Jen. I think that's all for today. And then you start from chapter 5, where we'll be dealing with the dead live load internal force calculation. Now we are getting into the members, into the members, what's going into the members, the reaction, the actual force, the bending moment, beam linear stiffness calculations, modulus of elasticity for the columns and all that. So that will create another section, and I hope I'll be able to explain in detail as much as possible. Thank you, Jen.
Okay, thanks so much. Good night.
All right, good night.
Thank you.